Hello everyone, welcome to Mutlu Learning Hub. Here is a situation many people run into in applied machine learning. A model looks solid in validation, the code is correct, metrics seem reasonable, but once you step outside that original setup, the behavior feels unstable or unreliable. When that happens, it's usually not a tuning issue or a bug, it's a modeling trade-off, specifically a bias variance problem. In this video, I want to focus on how to reason about that trade-off. We'll start by breaking down what prediction error is actually made of. Then we'll look at how bias and variance show up in model behavior. I'll explain why the trade-off is unavoidable. And most importantly, how to decide what to change next when a model isn't behaving the way you expect. The goal isn't theory for its own sake, it's diagnosis. When we are reviewing a model, one of the first things we keep in mind is that prediction error has multiple sources. If you look at expected error across different training samples, it can be decomposed into three parts: bias, variance, and noise. Bias comes from simplifying assumptions in the model. Variance comes from sensitivity to the specific data you are training on. And noise is randomness in the data that no model can fully learn. The key point is that we can't eliminate noise. What we can manage is the balance between bias and variance. Bias and variance describe how a model fails. Bias is about systematic error, how far the model's average prediction is from the truth. Variance is about instability, how much predictions change when you retrain the model on slightly different data. When we are evaluating models, we care about which of these two effects is dominating. A common way to visualize this is the target analogy. Low bias and low variance is what we aim for. Predictions are accurate and stable. High bias and low variance usually means underfitting. Low bias and high variance usually means overfitting. And high bias with high variance means the model is fundamentally struggling. This analogy isn't just illustrative, it helps build intuition for diagnosis. Here is the core trade-off. As model complexity increases, bias typically goes down, but variance usually goes up. Simpler models are more stable, but they may miss important structure. More flexible models can fit complex patterns, but they are often sensitive to the data they see. The goal isn't zero error, it's minimum expected error. Bias-variance trade-off shows up very clearly when you look at model behavior. With small data sets, a common pattern is high variance. The model changes a lot across retrains. In that case, regularization, simpler models, and careful cross-validation are usually the right direction. On the other hand, if a model is overly simple, bias tends to dominate. Then the right move is often to add signal, better features, interactions, or more flexible models. And one important reminder, more features don't automatically mean better performance. Assumptions need to be validated, not guessed. One thing we see often is treating underfitting and overfitting as root causes. They're not, they're symptoms. To diagnose properly, you need to look at behavior, training versus validation performance, and how stable results are when you retrain or resample. Labels don't fix models, diagnosis does. This is the loop we use when evaluating models. First, observe the behavior, training curves, validation performance, and stability across runs. Then diagnose whether bias or variance is dominating. Based on that, we decide what to change. If variance dominates, we look at regularization, simpler models, or validation strategy. If bias dominates, we look at adding signal or increasing model flexibility. After that, we re-evaluate and see how the behavior changed. That result feeds back into the next decision. The key is changing one thing at a time: data, regularization, or complexity, and learning from how the model responds. Bias variance isn't a theory problem, it's a decision problem. Good models don't come from chasing perfect scores. They come from making informed trade-offs based on evidence. Thanks for watching. If you found this useful, feel free to share or follow along for the next videos.